Good afternoon, everyone. I'm Haryadi Gunawi from University of Chicago, and I'll be talking about the case for limping-hardware tolerant clouds. And this is a joint work with my PhD student at University of Wisconsin, Tando. So let's start with the fact that hardware fails, and we know about this, that hardware can fail. And this is because of the growing complexity of technology scaling, manufacturing, design logic, usage, and operating environment. And because of this, hardware can fail in many different ways. They can fail stop completely. They can exhibit partial failures, like some sectors on the disk become inaccessible, or corruptions, maybe because of memory corruptions, disk corruptions, faulty processors. And there's a rich body of literature on this kind of hardware failure modes. But how about hardware whose performance degrade over time, right? This is what I call limping hardware. Does this thing happen a lot? So this is the first anecdote that I got back in 2009, and this is where it all began, how the research got started. So at Facebook, there's 1 gigabit NIC card on a machine that suddenly starts transmitting at 1 kilobit per second. Now, this slow machine caused a chain reaction upstream in such a way that the performance of the entire workload for a 100-node cluster was crawling at snail's pace, and technically, effectively making the systems non-available for all practical purposes. So I think there are two interesting cases here. One is that we have a case of a limping hardware, in this case a limping network card, and the performance degradation is quite severe. It's 1,000 times slower than its normal rate. Second is that there must be something wrong the way we build distributed systems, because suddenly now we have a cascading impact such that the whole 100 node is collapsing here. So when I heard this story, the first questions that I got is, really, is limping hardware common? Is cascading impact because of limping hardware common? So I started, talking with many more people, and turns out the answer is yes. For example, at Argonne, they have several storage units that had 4 servers having high wait times of I/O, and the maximum wait times was 103 seconds, and this was left uncorrected for 50 days. At CleverSafe, they find that sometimes the disk attempts to reread its block multiple times before responding. Again, at Argonne, on the Blue Gene clusters, they had a bad batch of optical transceivers with an extremely high error rate. And so this results in an effective throughput of 1 to 2 kilobit per second. And as I talk to many other people, pretty much many of them say, yes, we've seen this in production. And in fact, yesterday, one of my students sent me an email, and he said that I couldn't work today because the test bed is limping. So we use Emulab. And by the way, Emulab is just wonderful, and we are very happy Emulab gives us free resources. But this thing happened. So yesterday morning, in Emulab, there's a RAID controller that is working, but there are more than occasional timeouts and retries. It's running slowly. Pretty much the whole clusters continue to limp under the current mode. Okay? So we have a cascading failure. We have a limping RAID controller, becomes a limping testbed, and it makes my students not working yesterday. Right? Okay, so does hardware limp? I can say yes. Right? So we can have this definition that of a limping hardware, that is hardware whose performance degrades significantly compared to its specification. Is this a destructive failure mode? I would say yes. Again, there are stories about cascading failures, and there's no fail-in-place computing. And what this means is that if you have a limping hardware, users are directly affected. The administrator must run diagnosis tools to figure out which hardware is limping, maybe use segways in the data center to find the limping hardware and throw it out, right? And again, it's destructive because some of my students cannot work, okay? So basically, the whole point of this paper is to advocate, maybe this is time, that we should think about limping hardware tolerant systems. And as Jeff Dean from Google said, that anyway, reliability must come from the software. Right, so here's the outline of my talk. I'm gonna describe the impacts of limping hardware on cloud systems. I'm gonna describe limping failure analysis that we've done, and then some kind of lessons learned and more stories from the bug study that we performed. And then I close with discussion and conclusion. All right, so let's go back to this anecdotal impacts. So again, at Facebook, suddenly 100 node cluster was crawling. At Argonne, the whole GPFS file systems is in live lock because of just several limping hardware. So the question that we ask is why, right? How do we design distributed systems in such a way that we have these cascading failures? So this is the goal of our limping failure analysis. So we have two goals. First is that we want to measure the system level impacts. And then most importantly, we want to find design flaws. Okay? So in terms of our methodology, we target cloud systems like HDFS, Hadoop, Zookeeper, and we inject load to the systems and a limping hardware. For example, we're going to slow a network card on a one machine to maybe just 1 Mbps or 0.1 Mbps and so on. And we also perform white box analysis. We put lots of internal probes in the queues, threads, and so on, essentially because we want to find design flows in these systems. All right, so here's an example. We run a distributed workload, so you could imagine a 3-node write pipeline in HDFS. And what we're going to do is that we're going to measure slowdowns under no failure, crash, and a limping NIC. Okay, so for example, in the case of a no failure, the write works fine. It puts the data on the 3 nodes, and the slowdown is 1 because there's no failure. If we inject a crash, then there will be a timeout. After several seconds, there will be a failover, and then we can see that the systems react by putting the data to some other node, and you can see that the slowdown is, there's a little bit slowdown in the graph. But if we inject limping NIC, turns out in this case, what we find is that the timeout is not triggered at all. The write protocol limp to at the rate of the limping hardware. And if we inject more severe limping rate, like at 1 Mbps, 0.1 Mbps, you're going to see that the write protocol essentially just collapsed by orders of magnitude. Okay? So this is a template of the bars that I'm going to show. Basically, if you see this kind of uphill bars, this is bad. It means that there is no failover. Okay, so this is the results that I put in the paper. So we, again, this is initial work. We analyze Hadoop, HDFS, and HBase, run some workload. And in the case of no failure, slowdown is 1. And if we inject a crash, as you can see, there'll be a timeout failover. There'll be a little bit of slowdown. And then but if we inject limping rate in all these 3 systems, we see these uphill bars again, right? So it means that we can conclude that these systems are technically, they are fail-stop tolerant, meaning that they can deal with fail-stop machines, but they cannot deal with limping failures. They are not limping tolerant. As you can see, there is no failover recovery. Okay, so this is kind of the results that we show. So let me go deep to one of these systems, which is Hadoop, our favorite systems, and see why we have uphill bars here. Okay, so I think this is interesting because we know that Hadoop is tail tolerant, meaning that if you have a slow task, there's this thing called speculative execution that should re-execute the slow task in a backup task or speculative task in some other nodes, right? But when we see these results, we see these uphill bars, meaning that speculative execution is actually not triggered at all. Okay, so let's see what's the issue here. So let's consider just a limping network card on a map node. Okay, so the red circle here. So we have 3 map tasks, M1, M2, and M3. So if we have a limping network card, turns out that we found is that the speed of M2 is still the same as the speed of M1 and M3. Why is it the case? Because Hadoop runs on HDFS. HDFS respects data locality. So most of the time, the mapper reads input data from a local disk. So the network card doesn't affect the mapper in this case. But we all know the shuffling phase, basically in the reduce phase, these reducers needs to fetch data from the results from the map task, right? So in this case, all the reducers will be limping because all the reducers needs to fetch the output of M2. Now there will be no straggler in this case because all the reducers here are limping at the same rate. in Hadoop, a straggler is defined as a slow task, a task that is slow compared to other tasks of the same job. But in this case, since all the tasks are slow, there is no straggler. Speculative execution is not being triggered at all. Okay? But as you can see, now all the reduced tasks marked by the yellow nodes there are pretty much also limping because of one limping network card. So a couple of design flows, I guess, here is that first is that we only do task level straggler detections within a job. We don't compare performance across different jobs. And second here, once there's a single point of limping failure, because everybody needs to fetch the only data that is coming from M2 here, then there's no other redundancy, right? The only solution if we want to get out from this is to run the map test on another node reading from a different node, okay? Right, so, but that's not the end. So this is a work in progress. I'm gonna show you some results that we don't put in the paper right now. So on the last slide, you've seen that a limping network card leads to limping tasks, okay? And we found many other scenarios where we have limping maps and reduced tasks without any speculative executions being triggered, and we can talk more about that offline. Now here's the issue. If limping tasks use up all the slots, then we're gonna have technically another limping node, okay? Which means that the node is unavailable because all these tasks are pretty much running at a very, very slow rate because of a limping hardware in another node. By default, in Hadoop, there are 2 map tests and reduced tests that can only run at the same time. So if all the slots are being used, the node is technically unavailable. Now, if all nodes are technically unavailable because of the slots are being used, then we're going to have a cluster collapse. We're going to have a limping clusters. So I believe this is one reason for the story in Facebook. Okay? Right, so let me show you the kind of the implication here. So we ran a macro benchmark, Facebook workload. We ran it on a 30-node cluster. And in one of these nodes, we have one limping node with 0.1 Mbps. Now, the graph on the left here essentially shows the number of jobs that are finished over time, right? So if you focus on the green line, essentially things look good. You know, we are finishing jobs, hundreds of jobs over the spans of hundreds of minutes. But if you see the red line where we have just one limping node in the cluster, suddenly the whole cluster collapses. We can just only finish a very small number of jobs throughout these hundreds of minutes, okay? So why? This is exactly because of what I explained on the last slide, which is illustrated on this figure on the right. So the figure on the right shows the percentage of unavailable nodes in this cluster. And again, unavailable means that all the slots in that node are being used by a limping task that are affected by a limping hardware, right? So as you can see, at the same time, suddenly almost all the nodes are occupied with limping tasks, right? So technically, 30-node cluster is going down. And we try to analyze this on 60-node, same result, but the impact will happen a little bit later in time, okay? So as you can see, there's a cascading failure. We also try to run this, basically benchmark many cloud systems, Hadoop, HDFS, HBase, Cassandra, and Zookeeper. And we analyze many protocols. So as you can see, again, if you see uphill bars, this is not good, right? So it means that there is no failover, and many of the cloud systems here are not tolerant to limping failure, okay? So that's the kind of the results of our systems analysis. Again, the high-level point is that, again, one single limping hardware can basically collapse your cluster if we do not design our distributed systems in a correct way. Other than that, we also do perform a bug study, and I'll kind of share you some results from our bug study here. So we study bug repositories of Hadoop, HDFS, Cassandra, HBase, and Zookeeper. There are, again, we do some kind of filtering, and there are like 500 issues that pertain to failures, including fail-stop failures, corruptions, and so on. And we found around 53 what we call as limping-related issues. Okay? So let's see what happens in these issues. So I'm going to share to you the impacts of limping hardware that people see in production and the lessons learned from this bug study. All right, so first, turns out that applications and systems can hang or crash when we have a limping hardware. Perhaps in a good scenario, we have a very small number of threads, but if we have a limping hardware, suddenly given the same load, then we have too many threads working here. So the worker queues can grow without bounds, operating system can run out of threads, the systems can leads to out of memory exception. The systems can also be overloaded. Limping node is flooded with retries. Other nodes doesn't care that this node is limping. They also send lots of background jobs to the limping node. We also find cascading effects because of system designs, some kind of design flaws, I would say. So one example, sometimes when we build systems, we like to create what we call as multi-purpose thread. That is, we have one single thread here that has multiple purpose. First, it does background scan, but it also performs heartbeat to the master. So what happens is that if one of the disks is limping, then the thread is also limping. If the thread is limping, then pretty much the slave cannot send heartbeat quickly to the master, and the master declares the slave dead, although there are perhaps other many disks that are still good in this particular node. There's also this tricky queue management because requests get backlogged because of limping hardware. For example, imagine in a good scenario here where we have messages coming in, purple message for the purple node, blue is for blue, and maybe in a good situation, the queue is never full, right? But what happens if the node is limping here? There has been cases where the queue is full in this node because of a backlog request, and if this node is full, then other nodes cannot communicate to this node. This other node will have its queue full also, and then pretty much again the whole cluster can collapse because of this backlog request. Okay. All right, so those are our findings. So let me close with some kind of discussion and conclusion. So in general, what we find is that we found many limping intolerant designs. From our systems analysis, we find a single point of limping failure, coarse grain timeouts in HDFS, bounded threads and queues that leads to resource exhaustions, unexploited parallelisms, long log resource contentions, and so on. And again, this is in progress, and we are analyzing many more protocols. And from the bug issue study, I've told you about this tricky thread pool or queue management, limping oblivious background jobs. There's no throttling or back pressures, and so on. Right, so basically, the purpose of this paper is to advocate maybe it's time that we develop principles of limping anticipation, detection, recovery, and utilization. So for example, in terms of anticipations, maybe when we design distributed systems for every algorithms, for every data structures that we use, we need to anticipate limping cases, right? So we need to have limping tolerant design patterns. We might think about writing static analysis to find performance failure that can find limping intolerant data structures or algorithms. I also believe that it's time that we learn about statistical natures of limping hardware. So we are trying to work with this with industry. If we look at existing work, there has been lots of work that talk about memory failure, disk failure, and their statistical properties, but not so much on limping hardware. So I believe it's time that we should focus on this thing also. In terms of detections, I believe we should also be able to detect hardware in many levels, in the operating systems, in the distributed systems, and so on. I guess one of the challenge in terms of detecting limping hardware is that when we talk about performance, there is no hard errors. Performance degradation is an implicit situation, right? So if you want to have continuous monitoring, it might introduce lots of overhead. So we are also performing some study of, again, what are the explicit causes of limping hardware? Can we find these explicit causes to infer the implicit behavior, like error correcting, block remapping, and so on? In terms of recovery, as you've seen that, maybe it's better to crash than slow. So maybe there's one simple recovery strategy. Basically, what we want is that we want to be able to have a limping hardware to fail in place without affecting users and other nodes. Maybe we want to quarantine the limping hardware, but we need, I've heard stories that this is also not simple. For example, during an earthquake, you can have all the disks in your data center suddenly perform badly. You don't want to quarantine all the disks at the same time. So again, we need to think about limping recovery. And I think finally, utilization is interesting here, because if we think about fail-stop failures, we have the two extremes: either the hardware works completely or the hardware doesn't work. We can throw the hardware out, right? But in terms of limping, again, we need this study. Perhaps hardware can degrade between 1 to 100% for whatever reasons, and we need to decide what we need to do in between. Okay? And again, perhaps we need to have a cross-layer approach. There are many different hardwares. Again, switches, middle box, disk, processors, and memory. Perhaps we should tackle this at many different layers of our software stack. All right, so to conclude, if you look at decades of research, new failure modes always transforms the way we build systems. I believe limping hardware is a new destructive failure mode. In this talk, I've shown you the impacts, orders of magnitude slowdown, cascading failures, and there's no fail in place for current systems. Right? So again, maybe it's time for limping hardware tolerant computing. Right? That's it. Thank you. Thank you, Gideon.
Very interesting work. I have two comments. I don't know if it's a question or a comment. First thing is that I think one of the things that can tolerate this kind of behavior is the idea of having a non-synchronous distributed systems, in the sense that you cannot rely on your timers. So I found it surprising. For HDFS and Hadoop, it's not surprising to see this kind of behaviors, at least thinking in terms of this synchrony model. But for Zookeeper, they don't rely on the timers. I mean, they use the timers to change leaders or coordinators, but they don't rely on them. They don't trust on them. Could you share why it happens in Zookeeper?
Okay, yeah.
I don't know. I know it's not that.
Right. So basically, right. So we can imagine quorum-based systems as asynchronous in the sense that one limping node will not affect everybody, right? I mean, we can quorum. We get the quorum. So if we run a kind of a quick experiment, 20 seconds, we don't see the impact. But we do this white box monitoring, and we see there's a queue that keeps growing, and because of backlog requests, because the leader always tries to send the commits to that follower. Okay. So eventually, what happened if we run for 600 seconds with very high load? The leader just collapses because suddenly the queue grows, Java garbage collection kicks in, and if you have a leader-follower architecture, leader dies, the whole thing, the cluster collapses, right? Cassandra doesn't exhibit this behavior. It's not part of this talk, but Cassandra exhibits a very, very weird eventual consistency. If something is slow, it will just forget it. It will not even put it in the hints. It will completely never be eventually consistent unless you force the read repair on the systems. So that's why I think, again, this I don't propose detailed solutions, but I think it's interesting when we analyze these 5 cloud systems, how different designs. Zookeeper has a very clear semantic, but there's a clear impact. Cassandra has a weird semantic, doesn't have the impact, right? So let's see what will be the solutions.
Okay, yeah. It makes sense. Yeah. Just a comment. Zookeeper developers, they try to put a lot of effort in bounding these queues and dealing with them. Okay. Even in that, they had this problem. Okay. Yeah. Another thing is that it, in some sense, it goes against a lot of people that is mentioned that in data centers we don't need this non-synchronous fault model. But I think this kind of problem just shows that, in fact, if you rely on all your components, that all your components are fast, you can have this kind of problems, right? With timers and so on.
Yeah. Okay. Thanks.
Hi, I'm trying to draw an analogy between the limping hardware problem with general limping software or limping service degradation. So I'm thinking of the 10, 15 years ago, the slash dot problem was defined, and a lot of people tried to put effort in making sure systems degrade well with increased load. Do you see if there's any analogy in trying to solve that service degradation problem with the limping hardware problem?
Yeah, I'm even for myself, I'm trying to connect the two. I think the Hadoop case study is also like you could imagine the fact that speculative execution is there is to handle limping at the higher level of the software stack. But I think one issue is that if the software doesn't really care, thinks the hardware is a complete black box, then this thing will happen, right? So the speculative execution is just oblivious in terms of which hardware it's getting the data from, or transferring the data from, and these things happen, right? So I believe there are many lessons that we can learn from dealing with limping software, which I'm still exploring. But I believe it should be a complete, holistic approach when we try to, deal with limping failures. We should understand that the limping hardware itself. And I think when we talk about limping software, please correct me if I'm wrong, many of the issues probably deal with, 2x slowdown, maybe 3x slowdown. But in this, anecdotes that I found is that really, hardware is 1,000x slowdown because of error correcting, and I think that just changed the whole pictures of how we think about building the systems.
Yeah,
but yeah, good questions. Yeah, thanks.
So one last quick question. So it seems to me, and maybe I'm mistaken, I don't work too much in hardware reliability stuff, but from the difference between a crash failure and a limping hardware is the timer you put to measure the heartbeat on the system. If you are sort of aggressive in putting your heartbeat, then whether it's limping or crash, for the guy who's measuring the heartbeat, it should look like that thing crashed, so you work around. I understand in all systems it may not be possible to work around, but do you see that aggressive heartbeats might solve?
Yeah. There's been other work that shows that, again, I think like peer comparison, again, many people at CMU is working on this. I think the key is not like just basically constant value heartbeat, people say is always bad because we never know what the actual performance looks like. I think peer comparison makes sense, but I think many peer comparison works deal in terms of at the diagnosis level. But here I'm proposing that we should build fail-in-place computing for limping hardware itself. Yeah. Okay.
It sounds like a jackpot for a new researcher, right?
All right, thank you.